All right, this next section is an introduction to TS diagrams, where T is temperature and S is entropy. So on the lower left there, under section 6.2, you see an example of one. But I always like to, and this is also right at the very beginning of topic number 3, we do the same thing. But here's what I'm going to do. I'm going to take a pot of water, and I'm going to put 1 pound mass of water in it. When we all know there's about 8 pounds to a gallon of milk, so this is not very much water that I'm going to put in here. There's a pound mass of water. And now I'm going to add a flame to it and heat it up. And I'm going to plot temperature. Now the initial temperature that I had in here, when I put my thermometer in there, I put a thermometer in there. And I'm now going to read the initial before I got it started, and I plot it, and it was 80 degrees before I got started, 80 degrees Fahrenheit. And then as I plot it, I know, you have all done this before, I keep plotting temperature and temperature and temperature and temperature, and here's 150 degrees. And I keep going, and I know I get to 212 degrees, the temperature stops going up. And if I look down in there, I see this kind of swirling going on. That's going to be called microconvection, and we'll talk about that. But then what happens if I continue to add energy here? Here's the pot with the same pound mass of water in it, but the pound mass has increased its volume slightly, going from 80 degrees to 212 degrees. But this point right here now, we know I'm not going to see 213 degrees at atmospheric pressure. What's going to happen if I start plotting temperature? It's a constant until all the water is gone. Very key. All that I'm going to be doing is boiling the water at this point, and I start seeing steam come out, and I see the water go away. So this is all occurring once I get to this point right here. This is all occurring at 212 degrees. I never get to 213. It doesn't keep going up in temperature like this unless I have a pressure cooker. This represents atmospheric pressure and what happens to temperature of the water as I heat it up. And when it gets to 212, once I get to this point right here, the water is said to be saturated with energy. It is saturated. And then if you add any more energy to a saturated water or liquid, in this case, you're not going to heat it up anymore. You're going to start changing its phase. It's going to turn to steam. Very important concept. So a TS diagram takes this shape. Let's take a look at a TS diagram. Oops, went down a little too far. Hold on. A TS diagram. Here's temperature, entropy, and we can look, and I pick a pressure line. Here's an atmospheric pressure line. Then I know that when I did that turn right there, temperature is staying constant. That point right there represented, it became saturated. Now a phase change is occurring, and then I see it do that. This is very key. So I'm going to go ahead and put the dome in here like this. So this TS diagram, this area on this side here represents what's known as the subcooled region, SC. And when it's subcooled, our liquid is subcooled, I went from 80 degrees and I saw a temperature go up, and then I became saturated. Here, I was a saturated liquid. Then at constant temperature of 212 degrees, I vaporized that water. And at this point now, I'm still saturated with energy, but where this was a saturated liquid, this is now a saturated vapor. And if you add energy to a saturated vapor, you get up here, look at temperature starts to go up again, and you get what's known as superheated. Superheat. That's going to be all in chapter 3. That's going to be really cool. And it's kind of weird to see a line go up and then straight across and up again and go, well, what's happening to pressure? Well, this is all occurring at atmospheric pressure. And there's obviously an infinite amount of pressure lines. I can look at a pressure above atmospheric pressure or below atmospheric pressure. And they'll have all generally the same shape. If I looked at, if I was to plot something that is less than atmospheric pressure, it's going to come up, reach its saturation point, vaporize the fluid, go like that, and then I go to superheat. I could do the same thing above the atmospheric pressure line. So that's pretty cool. They're going to become very, very useful because we can put our entire cycle on there. One of our knowledge requirements, identify the relationship between heat flow during a process and a TS diagram representation of the process. So we can put our entire cycle on this thing. Watch this. This is cool. TS diagrams are pretty useful. And you can see that entropy is increasing in every single one of our processes. Let's put a big representation of a temperature entropy. And then let's put our four main components. Here's our reactor. Here's our turbine. Here's our condenser. And here's our pump. Well, let's see what happens. I know that at the discharge of the condensate booster, the feed pumps, temperature is going up. And at some point, it's going to enter the reactor subcooled. So there's the entrance to the reactor that it enters. And the purpose of the reactor is to raise it to a saturated liquid, and then it's going to vaporize it somewhat, and then we're going to remove all the moisture and try and get it all the way over here. So that as we go across the turbine, what we're going to do is this represents, say, the 1,000-pound pressure line. We can see that there was subcooled water coming in. The reactor raised it to saturation, then it vaporized it, and then it removed the moisture. This is a 1,000-pound pressure line. Way down here is our condenser pressure. And let's say this represents the 1-pound pressure line, 1 psia versus 1,000 psia. And so then an ideal turbine, and this is entropy, an ideal turbine could drop all of that energy across it and extract it and get useful work out. And this is a certain temperature, this is a certain temperature, this is a certain enthalpy, this is a lot lower enthalpy. Then the condenser can remove the latent heat of condensation, a new term we'll look at, but it is actually taking the vapor and turning it back into water as it goes this way. So that this pump that I have here, this pump can actually take a suction from it and pump it back up to the pressure that it needs to go. So you can see the whole cycle that we have on a TS diagram. The feed water system, from condensate to the discharge of the feed. We know we have feed water heating, and we have feed pump heat. So there is an actual sensible heat addition. And I'm still subcooled when I enter the reactor. The reactor will raise up the energy to saturation, vaporize it, remove all the moisture, come across a turbine by having a change in enthalpy, condense at a constant temperature, and then pump it back up. That's pretty cool. That's a TS diagram. And we're going to be using those over and over again, especially when we get to chapter 4 of thermodynamic processes. And the last thing we talk about on this page is heat capacity. Now, I'm going to introduce an equation where this is going to be very important, but this equation right here is a pretty important equation. It's one of the three biggies that we're going to use. And we should know what that is. That's mass flow rate in pounds mass per hour. And this is a temperature difference, and it's in degrees Fahrenheit. So I'm going to put that here. And this Q dot, well, Q is BTUs. This is the heat of my reactor. And a dot means per unit time. So this is BTUs per hour, which can be converted to watts. But I have pounds mass degrees Fahrenheit per hour. I don't have BTUs per hour. So the unit for this CP, that thing here, I know that it's got to be, well, let's see, it's got to be BTUs because I need one of those. And I need to cancel out pounds mass, and I need to cancel out degrees Fahrenheit. So you can see the unit for specific heat capacity is BTUs per pound mass degree Fahrenheit. Because by doing that, I get BTUs per hour. So what is this C sub P thing? Well, over on the right-hand side, section 6.3, you see heat capacity. It is essentially the ability of the working fluid to hold energy. Where C sub P, if I was to take this equation right here and solve it for C sub P, you can see that it essentially is proportional to this should be a big C because this is talking about the whole heat capacity. If I wanted a little c, I would say, little c, I only want to know what the heat capacity of 1 pound mass of water is in my working fluid. There's a little q divided by the change in temperature. This would be BTUs per pound mass, and this T would be in Fahrenheit, and there's my units, because I'm talking about 1 pound mass. Hey, what's the specific heat capacity of that 1 pound mass of water? And the unit would be in BTUs per pound mass degree Fahrenheit. A lot of times we say it's 1, not necessarily true. Go ahead and turn the page as we continue to talk about this. I think it's ultra important that we look at a couple things. If I was to take a look at atmospheric pressure and I was to go to this book right here, and I wanted to figure out the specific heat capacity of water, I can do it, and we'll do that. So we see that C sub P equals Q, or change in Q, the change in specific enthalpy over the change in temperature between any 2 points. All right, great. What does that really mean? Well, let's say I go back to that TS diagram. And I started at 32 degrees subcooled water, and I raised the temperature up by adding energy till I got to 212 degrees. If I was to look at the change in temperature right here, determining C sub P, I'm going to see the change in temperature is 180 degrees Fahrenheit. When I went from 32 degrees, when I went from ice to steam, the onset of steam, essentially. I have a saturated liquid right here. So I would have to add or raise my water, if it was at 32 degrees, I would have to add 180 degrees, essentially, to get it to 212. That's how much I'd have to raise the temperature. Now, if I want to look at the change in enthalpy, we're going to go back to this book, and I'm going to go to 32 degrees and look at the enthalpy at 32 degrees, and I'm going to look at the enthalpy at 212 degrees. And at 32 degrees, the enthalpy is, and I'm going to go to H sub F, right there. And you'll see 32 degrees. Come on, focus, camera. Well, I'll just tell you, it's about 0.01. And then if we go to 212 degrees, we'll see that it is 180. And the unit for it is BTUs per pound mass. That was the enthalpy. So C sub P is 180 BTUs per pound mass degree Fahrenheit divided by 180, or that's equal to 1. 1. C sub P equals 1 BTU per pound mass degree Fahrenheit. Such that one thing we know. What does it take to raise 1 pound mass of water 1 degree here to 33? Well, since I have 1 pound mass and I'm asking for 1 degree Fahrenheit, I have to have a heat addition of 1 BTU to go there. Another way of looking at it is if I want to turn this 32 degree water to saturated water, I have to add 180 BTUs to that pound mass. If I had 5 pounds mass, I would have to add 5 times 180. I'd have to add 900 BTUs to that pound mass to raise this up 180 degrees. So specific heat is essentially the ability of the working fluid to hold energy. And it's one of the beautiful things about water. It's abundant, it's cheap, and it has a high heat capacity, meaning it's good for absorbing energy and transporting it and converting the energy. There's a new equation on the lower left here. I'm going to point this out. Point this out right here. Very important equation, right? And we do have a knowledge requirement here, both in terms of defining specific heat capacity and the unit being BTU per pound mass degree Fahrenheit, and then being able to apply it in solving problems. So there's two equations we have where we apply it. And the first one I've already shown you was, okay, the rate of heat transfer in BTUs per hour is equal to, well, the rate at which we put the water into this device. If I don't put it very fast, if I only put 1 pound mass in there every 3 days, I'm not going to be transferring much heat. But if I put 10 million pounds mass per hour, well, that'll be a big deal. Now, here's what we see. We see the specific heat capacity times this temperature difference. So we can see if I have a higher flow rate or a higher specific heat capacity or a higher differential temperature, I can transfer a lot of heat. Well, that's one equation. There's some rules on this equation. Number one, no phase change can occur to use this equation, which means we can't use this in our reactor. We can use this in our condenser, but I can't use it. As steam is dumping into the condenser, there's a phase change. I cannot use it on the steam side of the condenser. Can't do it because there's a rule. No phase change allowed to use this equation. But what I can do, here's the circ water coming in, circ water leaving, and let's say circ water comes in at 70 degrees Fahrenheit and leaves at 90 degrees Fahrenheit. There's no phase change occurring there at atmospheric pressure. So if I assume that all of the heat that was transferred out of the steam was transferred in to the circ water, well, I could then, all right, I'll just solve for the heat transfer rate of the steam by solving for the heat transfer rate of the circ water. And I could use this equation on the circ water side. It's hot minus cold. Well, the hot is 90 degrees, I know it. The cold temperature is 70 degrees, I know it. If I assume the specific heat capacity is 1, I'm good. The only thing I would ask you is, hey, what's the mass flow rate of the circ water? And I can solve for the heat transfer rate of this condenser. So that's pretty cool. So we're going to be learning how to use this equation, recognizing no phase change can occur. I cannot use it in the reactor. I cannot use it on the shell side of the condenser, but I can use it in the tube side of the condenser. And we're going to see one other cool thing. One other cool equation. Well, we gotta memorize this one because it's not on our equation sheet. But when I looked at this TS diagram, and I had temperature and we had entropy, and it looked like that, and we saw temperature going up, then it became a saturated liquid, then it vaporized at a constant temperature until it became a saturated vapor. Then if you added energy to a saturated vapor, you would see temperature go up again, and it was superheated. Well, if I want to determine down here, when I'm less than saturated, this is called the subcooled region down here. This is subcooled. Anything less than a saturated liquid is subcooled. If I want to determine the enthalpy of a subcooled liquid, here's an equation. It is less than this enthalpy right here, and I can look this enthalpy up in my book. That point is called the F point. A lot of people like to say, okay, that's the enthalpy of the fluid. We call this one the G point, and misnomer, enthalpy of the gas. So what occurs here is a saturated liquid, H sub F, or fluid. When it is saturated, it vaporizes along this line all the way to H sub G and becomes 100% steam. And the difference between H sub F and G is called H sub FG, or the amount of enthalpy that you have to add to enthalpy rise that you'd have to add to 1 pound mass to turn it from a saturated water to a saturated vapor. So there's going to be 3 columns we look at, H sub F, H sub FG, and H sub G in our steam tables. And we're going to learn this really well in topic 3. But what about if I'm down here? Well, I know then I'm something less than the enthalpy of a saturated liquid. So it's going to be H sub F minus, well, looky here, the specific heat capacity times the temperature of the subcooled liquid, the temperature saturated minus temperature subcooled. So if this was atmospheric, this would be 212 degrees at this temperature right here. And then where are you? What temperature is the water would be the actual subcooled temperature. That would be this temperature. Well, let's solve this for C sub P. If I solve this for C sub P, what you're going to see is it is equal to the change in enthalpy between 2 points and the change in temperature between 2 points. And let's see what the unit for that would be. So if I knew, let me go ahead and erase this a little bit. So here, as I'm in a subcooled region, if I knew the enthalpy of the fluid right there once it becomes saturated, and I knew the enthalpy of the subcooled fluid, well, I could look at the difference between the two. And if I knew the temperature here of saturation temperature and the actual temperature of the fluid, the subcooled fluid, I could then plug those 4 things in. And the unit would be, look at here, enthalpy, specific enthalpy, BTUs per pound mass. And this unit is in Fahrenheit. So this is a cool equation to be able to remember as well. Enthalpy of a subcooled fluid minus specific heat capacity multiplied by the saturation temperature minus the subcooled temperature. This one's commit to memory.